recording. So as far as, so let's see, what's the situation with questions? All right, if there are no questions, let me review something about spherical Bessel functions. Remember, I said to you many times that I rather like spherical Bessel functions because they're so much simpler than cylindrical Bessel functions because of the greater symmetry of spherical coordinates. So to get to the right section here, I'm going to jump down here to this part. So Bessel's equation for the spherical Bessel function is this. And if you start out with an equation like this, minus Laplacian of V is k squared V, then, and you let V equal to R theta phi in this sense, then what happens, as we saw back in chapter 7, the equation, if we multiply both sides by R squared and then divide by V and multiply actually by, all right, R squared divide by V, actually multiply by minus R squared and divide by V, we then get this expression here because the Laplacian essentially factorizes. And the spherical part is a spherical harmonic. And we're left with this equation here, which I've reproduced over here. R squared, the R derivative of R of KL of R minus K squared R squared minus LL plus 1 R KL of R equals 0. So what we do at that point is we set R sub KL of R equal to JL of KR. And then we just substitute that in here. And we have, remember that the derivatives are R derivatives. So it's DDR of R squared, DDR of, so R prime KL is the R derivative then of JL of KR. And then the rest of the thing is just a straight substitution. And now what you see is you can put a K here and a K up there, K down here and a K up there. And so altogether what you've got is d by dx, and then you have K squared R squared, that's X squared, d by dx, JL of X equals X squared minus LL plus 1, JLX equals 0. So you get back to Bessel's equation. So what that tells us is that this is the correct solution for solving this differential equation. And sorry, let me remind you what the equation is. We don't have very much space to write it, so let me grab some space here and maybe pick, well, I'll go with black then for the moment. And the equation that we're solving here is minus Laplacian V equals K squared V. That's the equation that we're solving there. And so we can apply that to a particular situation. And this is the quantum dot problem. But it's much more general than that because this problem, the reason I'm doing it in detail again is that it illustrates a general feature of quantum mechanics and quantum field theory. One of the kind of puzzling features. namely that if you confine a particle to a small region, say a sphere of radius A, by a potential that's 0 for r less than A and infinite for r greater than A. But it doesn't have to be that potential. It could be just any potential that confines it to a region of size A. Then the energy is going to be proportional to 1 over A squared. And just generically. Now, of course, if the potential happens to have some, instead of being 0 and infinity, that is to say infinity, here, I don't know what color I'm using. Let's go with yellow for the moment. If we're talking about V equals, why this thing keeps going to eraser. So V is equal to infinity here, and V equals 0 there. All right, let's solve this problem, and then I'll digress on the generalizations. So what we want is that this, of course, then let me switch to maybe red. This is R KL of R. We want that to be 0 at A, and so in fact, what I should do is change that to A. So RKL of A is JL of KA. We want that to be 0, so we choose KA to be a 0 of the spherical Bessel functions. And I'm using the notation ZLN. There might be this reminds me of, and may exactly be, the notation of the cylindrical Bessel, the zeros of the cylindrical Bessel functions. But in any event, I'm saying that JL of ZLN is identically equal to 0. Let me just get rid of that. And so the equation then that what we've got is that the wave function outside the wave function for R greater than A is just 0 because the potential is infinite there. Inside the sphere of radius A, the potential is 0, and so you just have a free particle, and the Heisenberg equation for that is minus h bar squared over 2m grad squared psi equals E psi, or the Schrodinger equation. I don't know. Anyway, whoops. Multiplying then by minus 2m over h bar squared, we turn that equation into this. We identify k squared as 2m e over h bar squared. But now we know what k is. K is equal to z over a, and k is also equal to, k squared is 2me over h bar squared, and so we identify 2me over h bar squared with zln over a squared. That's this equation here that tells us what the values of k are. And these, in fact, we could call them KLN. So the energy ELN then is h bar squared over 2m times ZLN over a squared. And the point here is that the smaller the size of the volume in which the particle is free to move, the higher is its energy. And so that's a general feature of quantum physics, and you can see it examples of this in musical instruments. The smaller the instrument, the higher the frequency of the sound. And if you then go from, you then invoke Einstein's relation between energy and frequency, you then see, and then, well, switch to photons then. The smaller the region the light is confined, the smaller the region the photons are confined, the higher their frequency and therefore the higher their energy. The formula, of course, being E equals h nu, h being Planck's constant. So let's see, we haven't had any questions lately. I guess some of you have left for Thanksgiving. But the question needn't be a question. It could just be a request. In other words, a request saying, please explain this or please explain that. So I'm happy to do that, especially on a Wednesday. Any day I'm happy, but especially a Wednesday. All right, so are there any further questions about this? The reason I went through this in detail is that this kind of rationale occurs in quantum mechanics all the time. And excuse me. So that's why it's why I went through it again. All right, if we don't have any questions, then let me switch to let me just sort of remind you of what we did in differential equations, in particular the nonlinear equations of cosmology. So as I said to you yesterday, the general relativity 30 or 40 years ago, let's say 40 years ago, was a more mysterious subject. Black holes were thought to exist, but there wasn't a lot of their existence hadn't become obvious experimentally. No one had detected gravitational waves. The CMB was just beginning to be analyzed and measured, and dark matter hadn't yet been discovered, and dark energy hadn't yet been discovered. And so, of course, dark matter should be called transparent matter or invisible matter. But unfortunately, we've got that stupid term. And at that time, 40 or 50 years ago, general relativity then could, we could think of it as that its applications in cosmology could be arbitrarily bizarre. But now, 50 years have passed, and we found that the energy density of the universe is pretty much constant. It's pretty much a constant. Two-thirds of it is, just as far as we can tell, a constant energy of empty space, and then 1/3 is maybe, or 1/4 is an energy of invisible matter, and then 1/20th is the energy of atoms. And moreover, we've learned that space is flat, and there's nothing funny going on with time. And the only strange thing about space-time is that physical space, not time, but space is expanding with a scale factor that's been expanding, at least in our simple model of the early universe. It's been expanding from 0 or nearly 0 to 1 now. And the universe here is, as far as we can tell, flat. That is to say, the ratio of, well, little k is 0 or plus or minus 1, and measurements indicate that capital L is so huge that we might as well take little k equal to 0 and consider space to be absolutely flat. So the general relativity of cosmology has really become almost trivial. It's just that space is expanding, and of course it's expanding mainly because of dark energy, and we don't know what dark energy is. A few people think that the reason why we don't understand transparent matter or dark energy is that we don't really understand gravity, and that could be. It could be that general relativity will be extended in some way. But a lot of the structure of general relativity will have to be conserved because it's just obviously right. So these r, theta, and phi are what are called co-moving coordinates. To get the physical coordinates at any point, you multiply them by a. Well, you multiply the r part by a. Or you multiply any distance by a. If you now apply Einstein's equations with this metric, what you get is that the scale factor is accelerating in this way, where rho is the mass density and p is the pressure. And then over here, this is another of Friedmann's equations. This is a simpler one mathematically because it's only a first derivative. Again, mass density and, well, as I said, this k, you can, for practical purposes, set equal to 0. And I showed you some universes. Here are de Sitter universes, which are the case where you set rho 0 equal to some constant lambda over 8, a cosmological constant lambda over 8 pi g, g being Newton's constant. And so this is a case where the only thing in the universe is vacuum energy. And at present, the energy density is 2/3 vacuum energy. So the de Sitter universe is a good approximation now. And if we jump ahead another 20 billion years, it's going to be almost exactly the right answer. And you see, for de Sitter universes, what you can have is you can have a universe that essentially bounces. That's one possible description of the Big Bang. The other is one involving inflation. What seems to be the case is either we have a bouncing universe or we had a universe in which space at very early times was expanding extremely rapidly. You see this A here, this A can have a time derivative that's arbitrarily high. And in fact, you set k equal to 0. If you have a mass density that's sufficiently high, A gets arbitrarily high. There's no limit to the rate at which points in physical space can move apart. That doesn't mean that they're moving faster than the speed of light. It means they're moving apart faster than the speed of light. The point here is that if you were sitting next to one of these particles looking at it, you wouldn't think it was moving at all because you'd be moving along with it. And again, it's only that space is expanding. All right, I think I've said enough about that. So these were our various Friedmann, Lemaitre, Robinson-Walker cosmologies. If you have only radiation, the scale factor expands this way. You add matter, it expands this way, and then you add in dark energy and it expands more rapidly. This is up to the present, which is basically 13.8 billion years. If you go on further in the future, this thing is going to go up like that. It becomes an increasing exponential. All right, that's enough of that. Let me now give you some kind of an introduction to general relativity, which is a very nice subject, actually. But before I do that, let's see, do we have any questions? I don't see any writing in the chat box. And so if you want me to do this or that, it'd be good to ask before 6:20 when the class is supposed to end. All right. Now, if not, then let me mention what I think is one of the really important point that Einstein and others realized about 100 years ago, and it's that physical and mathematical points exist independently of the coordinates that we use to talk about them. Now, that's kind of obvious, isn't it? And when we change our system of coordinates, we change our labels for the points, but the points remain as they were because they're independent of the coordinates. And so taking that idea seriously, what Einstein said over 100 years ago was that the true equations of physics should be such that they apply and look the same basically in any coordinate system. So we should be able to change from one coordinate system to another, and if we do so, it should be, our equations should look roughly the same. All right, so I'm not going to go through this in super detail. Let me just make a few definitions now. And these definitions are ones that occur elsewhere in physics, in particular in our course in electrodynamics. We have fields that depend upon space and time, and these are vector and tensor fields. So let's first of all define what a scalar is. A scalar is a quantity that's the same in all coordinates. So you change your coordinates, your space-time coordinates, the quantity doesn't change. So the temperature at this particular point in the room at this particular time is the same in all coordinates systems. And in fact, the temperature then is a function of time and space. And if you change from your coordinate, x here, let me just say that x here is 4 coordinates here. In other words, as in special relativity, x0, x1, x2, x3. So the temperature at x, or some b at x, if some b of x is, if in the other coordinate system b prime at x prime is equal to b of x, then we say b is a scalar field, and temperature would be an example. You can think of other examples. I should think of other examples too, but I'm not quite sure what, it's a little hard to make sure that they're not hidden, they're not actually vectors. So let's think about the chain, about dx is here. So let me maybe come back to this, using this board here. So we have coordinates x, which of course is x0, x1, x2, x3. These are our 4 coordinates. And we might have dxk is just you know, for example, dx1, which would be x1 plus epsilon minus x1, which would just, I guess, be epsilon there. Anyway, if you change your coordinate system, then what happens to dx? Well, dx, let us say, dx prime or dxi prime is going to be partial of x prime I partial xk dx, hold on, dxk. In other words, it changes by essentially matrix multiplication. So what we have is that x prime is equal to a certain matrix times x, this x being x0, x1, x2, x3, and this could be x prime 0, x prime 1, x prime 2, x prime 3. So this vector is that, and this matrix is, well, this one is partial x prime 0, partial x0. That's the upper left element, and this one would be partial x prime 3, partial x3, the very lowest one, and then you fill them in according to this. This one would be partial x prime 0, partial x3, and this one would be partial x prime 3, partial x0, and so forth, dot, 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 and dot, 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 dot. Anyway, that's how these coordinate differentials change, and things that transform this way are said to be contravariant. And contravariant vectors, actually. And so an example is here, x prime I is a sum on k from 0 to 3, of course. So let me make that express. X prime k is a sum. Well, I changed I and k, so let me do I equals 0 to 3, partial x prime k, actually, partial x I, ai. And if this depends upon if the A are a field, that is to say, a field, you know, is something that something that's a function of x, which is to say t and x. And in fact, just to make it absolutely clear, this is what we're, well, whether we call this t and x, this might be, so let me write, for example, x is equal to ct and then position. Okay, in fact, maybe instead of calling it that, I'll call it r for position. So that's just an example. So fields are things that depend upon space and time, and a field that does this is called a contravariant field. And now the chain rule for derivatives, so let me switch to maybe a different color now. The chain rule for derivatives is right here. Let me move this over just a bit. So the chain rule for derivatives, of course, is that the partial with respect to x prime I is the sum k equals 0 to 3, partial with respect to xk, partial xk, partial x prime I. So that's just the chain rule. And that defines covariant vectors. So anything that transforms this way is called a covariant vector. And in particular, this thing here is a covariant vector field because it depends upon x. So for example, C prime I of x prime, sum k equals 0 to 3, partial x k, partial x prime I, c k of x. This is a covariant vector field. Now this stuff all gets generalized to tensors. So if you have something that's a tensor, for example, Fik of x, this might be the Faraday tensor in electrodynamics. So the Faraday tensor F prime, if we have that, this would be JL of x prime, and we're saying that it's covariant because the indices are down. And so this is then a sum on Ik equals 0 to 3, and it's partial xi, partial x prime j, partial x k, partial x prime L. So it transforms this way. So this is a covariant tensor. Of, and we might say of rank 2. You could say that this one here is a covariant tensor of rank 1. And if on the other hand, the indices are up, then the thing would be a covariant tensor, a contravariant tensor. Einstein's summation convention is that, so let me just switch colors here, namely that AI, BI is just defined as sum I equals 0 to 3, AI, BI. So this means that one can eliminate writing this all the time, and that makes the equations simpler to look at, and things that are simpler to look at are easier to understand. Same thing is true for names of things in science. If you call something an expectation value, the term is bad English. It's a bad translation of the German, and it's just a mess, and it doesn't mean anything to English ears. If instead you call it the average value, then immediately you see what it is. And so, for example, if you have some state psi and some observable S, then this thing is the average value of the observable S in the state psi. If you instead use this stupid term expectation value, then you've just added a dozen syllables and no meaning whatsoever because the grammar is wrong. The summation convention sometimes produces remarkable simplifications, and one of the ones that students like best is this one right here, namely that if you have in your expression something like this, then the chain rule tells you that this is just partial x prime I with respect to x prime L, and that's just the Kronecker delta. And if you then do it in you imagine the primed sense, so that you can think of it in a prime. Anyway, it's an invariant tensor. And here you see this is so here's the tensor in, let's say, our coordinate system. Now we switch to a new coordinate system, x prime, then we would, since this has one contravariant index k and one covariant index j, it's a tensor of rank 2, would transform this way, but by the summation convention, well, first of all, j has to be equal to k, and then we sum over k, and then we just get, by the chain rule, partial xi prime, partial x prime L, and that's just the Kronecker delta. So this is a tensor of rank 2 that's invariant. And so let's, I don't think I should try to do everything here. Let me, well, there are various notations for derivatives, and I became fond of the common notation because it was easier to write, but I don't know. I think maybe the better notation is this, because it's clearer than the common notation. So let me give you a little more insight into things. Let's imagine that P of X is a point in space-time with coordinates. So the point P is effectively a scalar because it's the same point in any system of coordinates. Remember, physical objects are things that are independent of our coordinate system. And so on the other hand, if we take the derivatives of that point, well, we're going to get our vectors that are covariant. So these we can think of as basis vectors. And if we change coordinates, then E prime I of X prime is going to look like that. And small changes in the point then are these basis vectors times small changes in the coordinates. So what I'm imagining here is that P is a point in our curved spacetime. So, and I'm imagining that our four-dimensional spacetime is embedded in some higher dimensional spacetime. And so that higher dimensional spacetime can be thought of as, so we can imagine that that there are vectors that are orthogonal to each other, in that this is just a higher dimensional Euclidean spacetime, and our curved spacetime lies in that. Now, one of the many things that Gauss did many years ago, a couple of hundred years ago, was to show that you could, in fact, understand the curvature of a surface or a space-time intrinsically. That is to say, you just can look at how points, the distance between points changes or depends upon their coordinates, and you can reveal to what extent the thing, the surface curves and how it curves. And so you don't need to imagine that your space-time, your curved space-time, is embedded in some higher dimensional space-time. On the other hand, although that's mathematically possible, I think it's intellectually far simpler to imagine that the sense in which our space-time is curved is that it's curved in a higher dimensional space. I think that I find that much easier to think about. That gives us a visual image, just as we can think of the surface of a sphere, a two-dimensional sphere, an ordinary sphere in 3 dimensions. Well, it's a curved surface in a higher 3-dimensional space. Now, what are these basis vectors? Well, the idea here is that there's that the dot product of these basis vectors is this metric of spacetime. And how do you define this dot product? Well, we'll be defining it simply as, let me go on just a little bit further. So I don't know, so in other words, when we say this EI of X dot EK of X is GIK of X, this being the spacetime metric, what we mean here is that the sum of these coordinates, so we have here EI alpha, EK alpha, and I don't know, 1 to D, depending on how big the space is that we're embedding it in. And there might be a sign here, sigma alpha. So in other words, we'd expect at least one minus sign here because the metric of space-time is has one minus sign. In other words, in empty space, GIK is just eta IK of X, which is the metric of special relativity, and then zeros everywhere else. And of course, actually what's happening is that this is, what we might say is if we want to do cosmology, then we would say we put a little a here, a of t. So this would be comma a. All right, let's see. I'm surprised we don't have any questions at all. So I see that you've adopted the names of the main atoms in the very early universe. I guess that's a very appropriate way of naming yourselves for some of this lecture. Suppose we think of V, some contravariant vector, and if we contract that contravariant vector with these basis vectors, what we've got is a scalar. And so what we can say is, let me maybe switch colors here. We can say that the partial of V with respect to xi would then be the partial of V, what did I, oh God, all right, it's L that I chose, so let me do, and so this is partial VI, partial XL times EI plus VI partial EI partial XL. So you see the derivative that's actually a covariant vector is more than this term. It also has this term, and this is called a covariant derivative. This was, I don't know when it came into physics first. It certainly was there in 1915 when Einstein did GR. It may have been there in formulations of electrodynamics before that, and it certainly in the 50s and 60s it was adopted by people doing gauge theory. And so since this thing is an actual vector, we're going to use dl of vk. We're going to define dl of vk as the thing that occurs here. And this is going to be the dot product of ek with partial v, partial xl. And when we do that, what we've got is, all right, let me just, since it has shifted to that, let me say that ei dot ek, this is gik, but e upper I dot ek, this is just delta ik. So these vectors are just designed to be orthogonal to those. So think Gram-Schmidt if you want. And so this dl of vk is then ek dotted into this partial derivative, but that was partial vi. Okay, what do I want? XL, all right, it's this one. Partial XL EI plus VI, partial EI, partial XL. And this with this is a delta function, so this is delta Ki. And what's left here is EK dot partial EI partial XL times VI. So this is partial VK partial XL plus EK dot partial EI partial XL times VI. Well, this thing is a special quantity which we call gamma. This was a notation introduced by, I guess, Christoffel. And this is gamma, and I would call it gamma K IL VI. Notice this means we sum I from 0 to 3 in this expression here. And so this is what's called the covariant derivative of a contravariant vector. All right, we're getting to the end of this hour, and I'm realizing that although I like to think of GR as having just a few simple ideas, there are several of these ideas. Each one requires a little bit of explanation, and consequently, it does take time, and we've pretty much run out of the 50 minutes. So we only have 3 minutes left. Let us, please, students, ask a question so that we, so that this isn't just me talking. Well, all right, let me switch colors then and go to the, that's strange, what's happening here? Let's go to a, well, you might, let's see, what, now what about covariant derivatives of covariant vectors? Well, again, we write this thing as a scalar, but now we write it as VK, EK, and we use the vectors that are perpendicular in the higher dimensional space to the basis vectors. And now we take a derivative, partial V, partial XL, and so this is partial VK, partial XL, EK, plus VK, partial EK, partial XL. And then we take a dot product of that with EI. And so we take a dot product with EI of this partial V, partial XL. And the EI with that, well, that's partial VK, partial XL, EI dot EK. Well, this is a Kronecker delta. And then we have VK, EI dot partial EK, partial XL. So this is partial VI, partial XL, plus VK, EI dot partial EK, partial XL. Well, you can relate this to gamma, and what we've got so far then is a formula for the ELF covariant derivative of V sub I, and it's partial VI, partial XL plus VK EI dot partial EK, partial XL. And it turns out, let's see, where do I show that? It turns out that one can show, it's done in the book, of course, that this is partial VI, partial XL minus gamma K IL VK. So this is the covariant derivative of a covariant vector. And just as vectors, covariant and contravariant vectors get generalized to covariant and contravariant or mixed tensors, so too you can take covariant derivatives of all kinds of tensors, and that's explained in these sections. And one thing that you can show is that the covariant derivative dl of GIK actually is 0. And I think I'll stop here because we're out of time. So I hope that somebody has actually been listening, even though that person or persons hasn't asked a question. I have the feeling that I've simply been talking to computers that have, whose users have clicked in the right place and then have gone off to read a book or make dinner or something. All right, well, happy Thanksgiving, everybody. The main thing is to stay healthy so that you're around to celebrate next Thanksgiving in a normal way. So remember, this is a deadly airborne disease, and so you should stay away from other people when you're indoors, especially when you're indoors. And the worst thing of all is a crowd of people indoors, like in a bar. Second worst, like in a restaurant. And all right, well, thank you, hydrogen. Hydrogen was the main atom in the early universe. All right, so I'll say goodbye and end the session now. Have a nice weekend, everybody, and I'll try to remember to assign new homework. That'll, of course, be due a week after Sunday. Okay, so let me stop share.
Thank you.
Thank you. And